Hello everyone, it is my great honor to give this presentation here. First of all, allow me to introduce myself. My name is Lin from Dalian University of Technology, China. The topic of my report is SHRIMP, a robust underwater visible light communication system. This work is collaborated by Professor Jie Xiong from University of Massachusetts, Amherst, USA, and Yongda Yu, Yichuan Zhang, Lei Wang, Guowei Wu, and Zhongxuan Luo from Dalian University of Technology. This is the outline of my talk. First, let me introduce the background. Underwater communication technologies are quite important for divers. In traditional methods, divers can only use gesture or tapping to communicate with each other in the complicated underwater environment, which is of low efficiency. Therefore, there is an urgent need for effective and robust underwater communication technology. Commonly, there are three traditional underwater communication technologies: acoustic communication, radio frequency communication, and laser communication. Acoustic communication technology suffers from large latency, high power consumption, and it is very expensive. Radio frequency communication technology has disadvantages such as severe attenuation and large size of antenna. As for the laser communication, it requires precise beam alignment and has some safety problems. Also, it is very expensive. Therefore, our challenge here is how to overcome the shortcomings of existing technologies and achieve robust underwater communication. As a potential 6G communication method, visible light communication shows merits in low power consumption and high data rate. Now, this technology has been widely used in air for data transmission for various devices, such as laptops, smartphones, and so on. And the IEEE has issued 802.15.7 standard for it. When using visible light communication technology, we can control the on-off status of LED to realize high-speed communication. At present, the data rate has exceeded 1 Gbps in the air. When we focus on developing communication technology in water, we should pay close attention to the signal attenuation. This picture shows the ability of water to absorb electromagnetic waves of different wavelengths. We can observe that the absorption of electromagnetic signals is usually large, but surprisingly, for the visible light, the absorption is quite small, making underwater visible light communication possible. Therefore, in this work, we will use the visible light communication technology to realize a small size and low-cost underwater communication system, which can provide illumination and high-speed communication simultaneously. However, we face some unique challenges in the complicated underwater environment. First of all, the continuous water flows move and rotate the transceiver, which can affect the data transmission of the visible light communication systems. Thus, achieving reliable communication that can tolerate the transceiver displacement and the rotation in the underwater environment is the first challenge. Also, in underwater environment, the sunlight interference can be strong. The water waves can scatter the sunlight, which produces severe interference for underwater visible light communication. What makes it worse is that, compared to the relatively stable sunlight interference in the air, the intensity of the scattered light keeps changing in the water. The intensity variation can span up to 2 orders of magnitude. Therefore, addressing the dynamic ambient sunlight interference in underwater environment is the second challenge. When visible light propagates in the air, the reflection is very little. However, due to the water flow and uneven salinity, the reflection in seawater is more severe, attenuating the received signal and accordingly causing large bit error rate and shorter transmission distance. Consequently, the third challenge is how to increase the communication distance in underwater environment. Next, I will introduce the system design of this work. We borrow the idea from mantis shrimp, which has extremely sharp vision in the sea. They use circularly polarized light and establish private channels to communicate with each other. Similarly, in our system, we also use circularly polarized light for visible light communication, so we call our system SHRIMP for short. We developed our system based on circularly polarized light and double links. The encoder, driver, LED, linear polarizer, and the quarter wave plate make up the transmitter. Then, optical filter, quarter wave plate, linear polarizer, silicon photodiode, IV amplifier, and the differential amplifier make up the receiver. From the transmitter to the receiver, natural light is converted to linear polarized light first, and then circularly polarized light, and finally linear polarized light at the receiver. In our system, the angles of two linear polarizers are perpendicular to each other to create clockwise and counterclockwise circularly polarized light, which makes double links possible. Then I will introduce the design of the transmitter and the receiver in detail. The transmitter encodes the data and converts the unpolarized light from LED to circularly polarized light. At the transmitter end, by using the commercial off-the-shelf LED and modifying the driver circuit, we can increase the data rates from 20 kHz to 120 kHz. Then we use linear polarizer to convert the natural light to linearly polarized light, and we use quarter wave plate to convert linearly polarized light to circularly polarized light. With the help of the circularly polarized light design, our system does not require tight transceiver alignment, and it can eliminate ambient light interference by the double link design. At the receiver, to address the sunlight interference, we use double links. Because two links are close to each other, so the environmental interference is similar in both links. Accordingly, we use the differential amplifier to eliminate interference and achieve robust communication. We also develop an underwater bipolar coding scheme called UBC, which is suitable for the double link communication. The design is complicated and I will skip the details. At the transmitter, the data is encoded by UBC, and at the receiver, the data is decoded. UBC has some advantages. It is suitable for the double link design. It has built-in ability to detect errors and prevent flickering. Also, it has a high throughput. Our system has a small size, a light weight, and is also relatively cheap. The hardware costs include 2 sets of LEDs and fabricated PCBs, polarizers and films, silicon photodiodes, IV amplifier and differential amplifier, and waterproof cover and glue, which lead to a total cost of about $77. The size of the device is 9 cm by 9 cm by 13 cm with a weight of 326 grams. We conduct experiments in different environments to evaluate the performance of the proposed scheme. The experiments are taken in different environments, including a 5 meters by 3 meters by 1 meter water pool, a lake, and the sea. When experiments are conducted in the lake and at the seaside, both transceivers are tied on the 2-meter iron rods. For deep water experiments, we place the transceivers on 2 underwater robots. In our experiment, we choose OpenVLC, a widely adopted visible light communication research platform for performance comparison, to explore the salient features of light in underwater communication. Besides the white color light, we also employ the blue color light to study the effect. In the air, OpenVLC has the advantage because it utilizes a better hardware component which can support a higher light on-off rate. However, in the lake water, the communication distance of our system can be up to 3 meters, whereas the OpenVLC only has a communication distance of about 1 meter. We also observe that the blue color light achieves a longer distance and a higher data rate in the water, which is quite different from the result in the air. Therefore, we can conclude that in the underwater environment, the performance of the proposed scheme is better than OpenVLC. Then, to demonstrate the advantages of double circularly polarized light links over one single circularly polarized light link, we evaluate the performance difference in an indoor water pool. As shown in the right figure, one link achieves a shorter communication distance comparing with the double links. The reason is that when we only use a single link for underwater communication, it cannot combat ambient interference as it does not have two physically close-by links to remove the common interference. To demonstrate the advantages of the circularly polarized light over linearly polarized light, we compare the performance of shrimp when it is implemented with and without the wave plate. The key difference between circularly polarized light and linearly polarized light is that a slight rotation of the transceiver will lead to link misalignment when the linearly polarized light is used, which is not an issue for the circularly polarized light. As shown in the right figure, we can see that unpolarized light is also not affected much by the rotations. However, unpolarized light is still not a good candidate as it can be more severely affected by the ambient light, which is also unpolarized. Finally, we come to the conclusion of this paper. First, we exploit the circularly polarized light and the double link for underwater visible light communication technology. Second, a coding scheme named UBC, tailored for underwater communication based on double circularly polarized light design, is developed, which achieves low bit error rate. Third, we prototype shrimp on commercial off-the-shelf LEDs with fabricated printed circuit boards, which only costs about $77. Fourth, extensive experiments conducted in different environments demonstrate that shrimp can combat against environmental interference and achieve robust communication in underwater environments. Okay, thanks for your listening, and this is the end of my talk.